Welcome everyone for this last session about symmetric cryptanalysis. Not the last session of the day, but last session about symmetric cryptanalysis.
The one and the only one. Exactly.
The first talk is about Grosvenor basis analysis, and Luca will give the talk.
Okay. Thank you so much. Good morning, everyone. So I'm glad to be here. Today we'll present our work, Grosvenor basis cryptanalysis of an MOE. This is a joint work with Arnav Roy. So we will start with a brief introduction about the context, and then we will move to a background on the Grosvenor basis and on the Grosvenor basis attack methodology. Then we will deal with the MOE cryptanalysis and our contributions. So a brief introduction. Now we are working with advanced cryptographic protocols, for example, zero-knowledge proofs. And here we need efficient hash functions over large primary fields, not only over F2, for example. And so the name under which we can call all those primitives is arithmetization-oriented primitives. The natural algebraic representation means that the algebraic attacks are the main threat to deal with. So let's start with a brief notation that we will use during the slides. So K is a finite field, R denotes a polynomial ring, so the set of polynomials in n variables, x1, xn, with coefficients in K, and I will denote an ideal, and X, for sake of simplicity, bold X will denote all the set of variables from x1 to xn. Okay, then let's move to the Grosvenor basis background, very brief introduction. So when we write a polynomial, we know that we need to sort the monomials inside. Okay, how we can sort this? With a monomial ordering. In particular, we are interested in a total order and in a well ordering. So every time we have a set of monomials, there will be always the smallest element. But here, in this work, we were mainly interested in two monomial orderings, DRL, degree reverse lexicographic, where we take the tuple of exponents associated with a monomial, we compute the sum of the exponents, and then we compare these two sums we have computed. Okay. If there is a tie, we solve the tie with another monomial ordering, in this case with the reverse lexicographic. Then the other one is the weighted monomial ordering, which is nothing else the same we have seen before, but weighted, in the sense that the sum of the exponents is weighted depending on the variable associated to the certain exponent, to a precise exponent. So for example, if we have x squared, y squared, the sum in the DRL is 4. If we have x squared, y squared, and the weight of x is 2, then the sum is 6. Okay, then how we want to compute a Grosvenor basis. Now we have a set of polynomials, an initial set of polynomials, and we want to define a new set of polynomials, which is nice in a certain way, and that helps us to solve the polynomial system. And so we want to compute a Grosvenor basis. In particular, we are interested in the reduced Grosvenor basis, so where we deal only with monic polynomials, and there are no monomials in the polynomials G which are divisible by the leading monomials of those polynomials G. Okay, how we can compute this Grosvenor basis? I mean, the first algorithm was the Buchberger algorithm from the University of Innsbruck, and first of all, the main component are the S polynomials. So we compute the S polynomials, and then what we do is that we reduce those S polynomials by the other polynomials we have in the Grosvenor basis. If the result is 0, if the remainder is 0, then we don't need to keep these S polynomials anymore. But if the remainder is not 0, we take the remainder and we put this inside the Grosvenor basis G, inside the set. In this way, we build another set of polynomials, which is our Grosvenor basis. But how can we stop this computation? Well, we can use the Buchberger criterions. There are more than one. This is just one. And then we can make it a bit more in the deep. But this is very important. So the Buchberger criterion tells us whether we need to compute an S polynomial or not. Okay, perfect. So let's go now to the Grosvenor basis attack methodology. We start usually with a primitive. We take one primitive. In this example, you can see the nonlinear layer of an MOE. And what we do is that we model the primitive as a set of polynomial equations. Okay, now we want to compute a Grosvenor basis. And usually we take the system we have defined, we apply an algorithm like Buchberger, F4 on F4 or F5. Then we can follow two main ways. And now we want to compute the univariate polynomial that helps us to find the solutions. And how we can compute these univariate polynomials? We can use basis conversion, which is the typical technique. So we can use, for example, FGLM, or we can use eigenvalue methods. In particular, we are going to compute the determinant of the multiplication matrices associated with the target variables. Okay. Other than the determinant computation, we can use also the Wiedemann algorithm, and we will see that by using the Wiedemann algorithm, we can exploit the sparseness of these matrices. And then at the end, we have the univariate polynomial. We find the roots. We can use, for example, the Kaltofenschub, or if we have a small prime field, then we can use the GCD with the field equations. We can choose different techniques. Perfect. But here we have some problems. Here, for example, we have the degrees of the equations. After the computation of the Gromnak basis, are the degrees of those equations small enough? We don't know. Are those polynomials sparse or dense? We don't know neither. And the complexity of the algorithms we have here is pretty high, in particular for the GB computation and for the univariate polynomial finding. And another thing that I want to stress out is that here we have loose theoretical bounds. Especially for GB computation, we have the Macaulay bound, which tells almost nothing about the real complexity of the step. So usually what we do is that we take a primitive, we compute the complexity, the Macaulay bound, and then we decide the number of rounds. Well, we will see also in this case that is not useful. Why? Because we have not concrete bounds. Sometimes it can happen that the complexity can be very high, but the real complexity is very low. We will see here that it is polynomial in an MOI. And now go to an MOI. So an MOI, okay, now it works, is a zero-knowledge range permutation presented in Crypto 23. And it is defined over K, which is equal to FQ, where Q is a prime, or 2 to the n, so a binary extension field. And here we have two parameters, L and alpha. L denotes the number of branches, and alpha denotes the simple power function, the degree of the simple power function in the non-linear layer, which is equal to 3, 5, 7, and 11 by reading the paper. And then it works over an even number of inputs and outputs an even number of values. Each round is composed by a linear layer and a non-linear layer. Sorry. OK, then here we will focus on the odd characteristics, so over FQ, where Q is a prime. OK, this is the non-linear layer of an MOI. Here we have three main functions, Q gamma, e to the power of -1, and Q delta. E to the power of -1 is x to the power of 1 over alpha. But of course, in our polynomial modeling, we will use this version. So we will use e because it is x to the power of alpha. Q gamma and Q delta are 2 degree 2 polynomials. OK, an MOI is mainly used in sponge constructions. So what is the problem we will use to define the security is the SICO problem, so constrained input, constrained output. OK, let's go to our contributions. This is an example with L is equal to 1 and alpha equal to 3. I'll show you how to create the polynomials of the model with L is equal to 1 and alpha equal to 3. But this works for whatever value of alpha and whatever value of L. And this is the first time it happens. OK, we have, for example, the SICO problem. We fix alpha of the inputs to be 0, and we fix alpha of the outputs to be a certain value. In this case, we can put, again, 0. OK, what are the security implications here? Here, we know that hash functions rely on 3 main properties, so preimage, second preimage, and collision resistance. And here, we want to find the solutions to this polynomial system we have defined before. So the number of solutions can tell us what we are breaking. So if we have more than one solution, we are breaking collision resistance. If we have only one solution, we are breaking preimage resistance. OK, if you have more than one, preimage is implied. OK. Now, let's start here. So the first contribution is the definition of a new model of representing an MOI, which we called ASICO. And how we obtain the equations. The first equation links the second output of the linear layer with the input to the function e and the second output of the nonlinear layer. Then we go to the second equation, where we link the 2 outputs of the linear layer with the output of the function e. And then we move to the third equation type, which are the constrained outputs part. So we link the two outputs of the nonlinear layer together, and we fix the constraint to be 0 because we have the SICO problem. OK, so now we can define our ASICO model. We take all those polynomials together, and then now we obtain L times 2n plus 1 equations in L times 2n plus 1 variables. Why I'm stressing out that we have a determinate system? Because then when we will compute the Gromov basis, we will see that we will obtain more equations than variables. OK, and now we move to the GB computation. So we want to prove the GB complexity for L is greater or equal to 1. So for whatever number of L and whatever value of alpha. And these are the results. For alpha is equal to 3, we can use the degree reverse lexicographic order. So here, for example, you can see that we can obtain this nice structure where the variables y and s have degree alpha, and then we have the couples. OK. And then we want to use a weighted monomial ordering to deal with alpha is equal to 5, 7, and 11. I mean, this also, the weighted monomial ordering works also for alpha is equal to 3. And here we obtain, again, almost the same structure of the polynomials, but the y variables have degree 2, and the s variables have degree alpha plus 1. So as you can notice, we have more equations than variables, but this is nice, because this helps us to reduce the quotient ring dimension and to prove what is the maximum degree that the univariate polynomial at the end will have. OK, now why a weighted monomial ordering? We want to stop. The idea is that we look inside the Gromov basis computation, in particular in the Buchberger algorithm, and we see how can we stop the reductions in the middle. OK, here we have, for example, with alpha is equal to 5, we have that s11 to the power of 5 comes before y21 to the power of 2. This is the DRL. So what we want to do is, why not to do this? This will stop all the subsequent reductions. OK, perfect. Let's choose some weights in this way. So 2 times the weight of y should be greater or equal to alpha times the weight of s. OK, and this is what it happens. Now we stopped the subsequent reductions, and in this way we can compute the Gromov basis also for alpha is equal to 5, 7, and 11. OK, these are, for example, small-scale experiments with 31-bit prime. You can see that for alpha is equal to 3, 5, 7, and 11, we were able to compute the Gromov basis for full round instances in milliseconds. And we were able also to go to 100 rounds in milliseconds, but we stop at a certain point, I mean. OK, so let's see at the complexity. We prove the structure because we can prove this complexity by construction, because it is just following the Buchberger algorithm. So we can literally compute and count the steps required by the Gromov basis algorithm. And here we can see that both the complexities are polynomial in L, so the number of branches, and linear in N, the number of rounds. OK, now we move to the second step. So the univariate polynomial finding step, where we can employ 2 different techniques, the eigenvalue methods or the FGLM. But here, what we want to do is that, OK, the complexities of those steps depend on 2 main variables, the sparsity and the I, which is the quotient ring dimension. So first of all, now that we have proven the Gromov basis complexity, we can prove the quotient ring dimension, and we can precisely define the complexity of those steps. OK, exactly. What I said is that we have proven the quotient ring dimension, which was conjectured in previous works, not only for L is equal to 1, it was conjectured only for L is equal to 1, but this proof works for whatever parameter. OK, as I said, the proven GB structure of an MOE implies proving the I. It's very easy. But now, I told you before that we want to exploit the sparseness of these multiplication matrices, so can we compute the sparsity of these matrices? And can we interpolate those values to see how this sparseness is increasing in a certain sense? OK, yeah, we can. And thanks to this, we can see that the complexity is getting lower. And for example, for L is equal to 1 and alpha is equal to 3, we are below the security claim. And also for alpha is equal to 3 and 5 in the 256 claim bit security. The gray boxes are the reduced round complexities, in the sense that what is the number of rounds for which the security of the primitive is below the claimed security. OK, and now the FGLM. Does it make sense to apply FGLM to this primitive? This is a good point, Because usually what we do is that we apply FGLM. Why? Because we go to the shape form. And the shape form has this nice structure where we have one univariate polynomial, and then we can easily recover all the other solutions. Yeah, that's true. This is what has been done, usually is assumed. Often in the cryptanalysis, this shape lemma is assumed. Why? Because we have a constraint. Let I be a zero-dimensional radical idea. It is not easy to prove that it is radical. Usually, it is not. So we need something more. And what we have done is that we have proven the shape lemma for an MOE, but in general, for zero-dimensional ideals. And this is very nice, because now this gives us a possibility to say that, OK, every time we apply FGLM, in particular sparsity FGLM, for example, we obtain a shape form. And then we can recover easily the solutions. OK. A summary of the results. So what we have done is that we have defined a new polynomial model for an MOE. This polynomial model gave us the possibility to compute the Gromner basis complexity for whatever parameter. And then what we have done is that we have applied the Wiedemann algorithm to exploit the sparseness of the multiplication matrices. And then we have obtained new security bounds. And regarding FGLM, other than proving the quotient ring dimension, we have proven the shape lemma for zero-dimensional ideas in general that has no solutions at infinity. Thanks for your attention. If you have any questions, thank you so much.
Thank you for the talk, Luca. Is there any question in the room? If so, you can come to the mic. Please ask your question.
Can you go back, please, to the sparsity formula you had?
Yeah, sure. This one.
Yes. So is it a theoretical analysis? Is it experimental?
This is experimental, exactly. It was conjecture by taking a lot of results from the experiments, and then we interpolate the results. It would be very nice to do property testing on this kind of stuff, and being able to define the sparseness as a function of what we have, for example, of the number of monomials we have in the polynomials defining the system. It would be very nice, this kind.
Right. Now, looking at it, the exponents, the multiples of n in the exponents seems to be very small. So what property of the anemoy definition are leading to such sparseness?
Let's look at the polynomials, then
Okay.
I can show you. Again, everything is done by those equations. Those equations are, if you start computing this, at the beginning they are linear, and then they are starting growing, but the degree is so low that what happens is that we are, when we compute the S polynomials, we are not creating so many monomials, and that is the reason why when we compute the multiplication matrices and we do the reductions, we are not creating so many monomials, and so this is the reason.
Could you make a simple change that will greatly increase the density?
Exactly. The point is that here, if we make a simple change just to create a lot of monomials, what happens is that we are reducing the efficiency of an MOE. That is the main point. And this works also in other primitives, because usually we want to keep the efficiency as accurate as possible, and it's always a balance that we need to.
Thank you.
But you're welcome.
Yes, so you seem to benefit from this weighted sort of metric on monomials. So does it allow also to work on sparsity, so that, for example, the weighting allows you to optimize the initial sparsity in Gromner basis?
Exactly. What we can do, if we analyze the polynomials inside what happens during the Gromner basis computation, if we do it with DRL, for example, what happens is that we are creating a lot of reductions. These reductions are creating a lot of monomials, and we want to stop them. So the weighted monomial ordering is helping to improve the sparsity of these multiplication matrices.
Okay. So the second question is, can you use it more than once? For example, you partly define your weighting, and then you do some Gromner basis computation, not to the end, and then you can adjust. Can you adjust the weighting in order to improve the sparsity in the middle of this computation?
You can do this, exactly. One thing that can be done is that you set a set of monomial weights, you compute a Gromner basis. After you have a Gromner basis, maybe you want to do something more. You want to go directly to the solutions. Maybe there is a clever way to go to the univariate polynomial. That could be. In this case, it does not happen. But what can happen is that maybe if we can now modify the sorting of these monomials in our Gromner basis. We recompute the Gromner basis with respect to a new monomial ordering, and then we obtain something more. That would be very nice.
Thanks, Luca. Very nice work. So a number of people wonder about the security of Poseidon.
Yep.
Could you comment on whether any of those ideas may be applicable, because the security margin seems to be large so far?
That's true. Yeah, exactly. The main problem with Poseidon are the extensions with the SICO K in general. So usually we work with SICO 1, SICO 2, SICO 3, and so on. And in SICO 1, we know a technique, which is interpolation, which is easier to deal with in this case. But when we move to SICO 2, for example, and so on, then it's a bit tricky. Regarding the Gromner basis computation, yeah, I can tell you that, yes, using monomial weights helps to compute a Gromner basis for SICO 1 and SICO 2. Yeah.
Thanks.
You're welcome.
Okay, thanks the speaker again, and we will move to the second talk.
Thank you so much.
So the second talk of the session is about SHA-3, and Zhang will give the talk.
Okay, thanks for the introduction. I'm Zhong Yizhang from Institute of Information Engineering. My topic is pre-image attacks on up to 5 rounds of SHA-3 using internal differentials. This work is done together with Qingyan He and my PhD supervisor, Mei-Chen Liu. My talk will be divided into these steps. Let's start with some background and also the previous work and our contribution. A hash function is a symmetrical algorithm that takes an arbitrary length input to a fixed length David digest. In cryptographic domain, it should follow some security properties. One of them is pre-image resistance, which is that if given a digest H, it should be difficult to recover the pre-image message such that big HM equal to H. In our attack, we focus on the pre-image attack. This is short description for Kuchak. Kuchak is one of the most important algorithm in hash function. After MD5 and SHA-1 were threatened, NIST opened the SHA-3 hash function computation in 2007, and it was submitted to the computation in 2008. Its designers are Bertoni, Diamond, Peters, and Asha. 4 years later, it became the winner in the competition. And in 2015, Kuchak was standardized by NIST as SHA-3. SHA-3 has 6 versions, including SHA-3 224, 256, 384, and 512, and 2 extendable output functions. Kuchak adopted the sponge construction. The sponge construction as a framework of constructing hash function by permutations. It uses bit underlying permutation. Kuchak F contains 24 rounds. And there are 2 parameters, bit weight R and complexity C. The sum of R and C is B. And before processing, the message is repeated and then spelled into R bit blocks. For SHA-3, it has an internal state of 1,600 bits, which can be seen as a 5x5 matrix, where each cell is a 64-bit line in the direction of the axis. And its round function consists of 5 steps: theta, rho, pi, chi, and delta. The linear layer is the first 3 steps. and chi is the only nonlinear operation. Okay, let's look at some previous work. Firstly, in MPS13, the authors apply rotational cryptanalysis to achieve first pre-image attack on 4-round key-check. In GLS16, a 2-round linear structure is proposed, which is one of the major tools for security evolution of SHA-3. And in 2022, Diner proposed a polynomial method-based algorithm for solving equation systems, which achieved the best 4-round attack on key-check 384 and key-check 512. In Botany 10 and CKMS14, the author used algebraic techniques to speed up brute force pre-image search for up to 9 rounds of key-check. As we know, the best-known pre-image attack with more than a tiny advantage over a brute force search currently only research 4 rounds. The table summarizes some results of pre-image attacks. The last row shows our analysis. The major contribution is that we use squeeze meeting the middle attack to propose pre-image attacks on up to 5 rounds of 6 SHA-3 versions. In particular, pre-image attacks on 5-round SHA-3 224, 256, and shake 128, and shake 256. The second part is overview of the attack. One of the methods we used is meet in the middle attack, which is proposed by Defay and Hellman in 1977. It is an efficient, exhaustive search way based on the birthday attack. The idea is to divide the whole space into 2 parts and find a collision between them. And a typical example of the application is to attack the block cipher with double encryption. Meet in the middle attack can be used to perform pre-image attacks on sponge-based hash function. The attacks use multiple blocks of messages and find collision in the complexity part. Finally, they need to modify the value of the middle block of messages to ensure the entire state compatible. Squeeze, the second method we combined is squeeze attack, which is proposed by Dina, Denkuman, and Shamir in 2013 to perform collision attacks on round-reduced key-check. The idea is to select subset S and D from the input space and output space so that the elements in S can be mapped with a certain probability to the output subset D. Since the size of D is smaller than the output space, it can gain an advantage over the burst attack. In this work, we combine squeeze attack with meeting the middle attack. We divided the mapping in 2 parts, and the input subset in the 2 parts are mapped with a certain probability to the output subset in the middle. And we use squeeze attack to find a collision in the middle subset with an advantage over the burst attack. Squeeze meeting the middle attack can be used to perform pre-image attacks on sponge-based hash function. We also select multiple blocks of messages and find a collision in the complexity part. And finally, we modify the value of the middle block to ensure the entire state captable. The difference from the general meeting the middle attack is that in the complexity part, we preset the internal difference to launch the squeeze attack with an advantage. Actually, we only needed to find a collision on half of base in the complexity part because the other half parts is same because they have the same output difference. The big dirt out. Next, we will briefly introduce internal differential cryptanalysis. In standard differential cryptanalysis, we consider two messages and the evolution of the difference between them. However, in internal differential cryptanalysis, there is only one single state, and we are tracking the difference between them. For generalized internal differential cryptanalysis, a single state is divided into multiple parts, and we consider the difference between one part and the rest parts. In this work, we are focused on the internal difference between two parts of a single state. This is a special type of states. If one state has period I in the z-axis, which is called a symmetric state, the fundamental period corresponding to I is the greatest common divisor of I and 64. I can attain non-trivial values of 1, 2, 4, 8, 16, and 32. Here is an example of a symmetric state with period I equal to 16. Now let's introduce the concept of internal difference sets. Given a period I, if the set by adding a single representative V to all symmetric states is an internal difference set, which is called internal difference for short. If V is zero vector, the set is called zero internal difference, which is actually the set of all symmetric states with period I. Is a similar case to question group. The action of linear mapping on any internal difference is equivalent to acting on the representative state. Now let's see the framework of the attack. For 5-round pre-image attack on SHA-3, our attack is divided into 3 phases: forward phases, backward phases, and collision phase. In forward phase and backward phase, we utilize internal differential characteristic to filter the states with the same internal difference in the competitive part. And in collision phases, we find a collision in the competitive part. And finally, we modifying the multiple block of messages to ensure the entire states capable. Now let's introduce the basic techniques for short. The first technique is target internal difference algorithm. Target difference algorithm is proposed to contrast the connector in a collision attack. An end-round connector is actually an algorithm to output messages satisfying the following three conditions. And in internal differential analysis, this problem can be transformed to internal connectivity problem as the following formula. In forward TIDA, this problem can be transformed into solving linear systems. And in backward TIDA, we transform the problem to lookup tables. For backward TIDA, we defined the value difference distribution table. The purpose is actually to estimate the complexity of the backward TIDA. The second technique is the linearization of the inverse S-box. So in the operation, we found that if we want to linearize the inverse operation of Q-check S-box, we need to add at least 3 linear conditions to the value space. The case is similar to the case in forward phase. And the detail of the technique can refer to the paper. The last technique is based on Sasaki's analysis in 2014 of unbalanced meet-in-the-middle attacks, since the cost of obtaining a state through forward phase and backward phase is different. We adjust the number of messages required in the forward and backward phases to minimize the overall complexity of the attack. This is the last part, results and a summary. The table lists our results of pre-image attacks on run-reduced 6 SHA-3 versions, including the parameters of internal differential characteristics. In this page, we present a small cell example of pre-image in Q-check function, where the digest is all one base. The parameter of internal differential characteristic shows on the right, and the theoretical time complexity is 2 to the power of 34.25, and the experimental time complexity is 2 to the 35. Okay. Let's see the summary and the future work. In our work, we utilize the squeeze meet-in-the-middle attack to find a pre-image for up to 5 rounds of all the 6 SHA-3 functions. We present the first pre-image attacks on 5-round SHA-3 224, 256, shake 128, and shake 256. And present the best pre-image attacks on 4-round for 5 versions in SHA-3. Interesting future work is to find better internal differential characteristics by MLP or set to reduce the complexity or extend the attack runs. Another work is to apply internal differential analysis to other ciphers. Okay, that concludes my presentation. Thank you for your attention.
So thank you, Zongyi, for this technical talk. Is there any very short question? Yeah.
So in this type of attack, do you use the undisturbed bit property of the scan?
You mean I use some bit?
Yes, so when you work on these differentials, do you use the so-called undisturbed bit property of the S-box?
Yes, in the linearize of the S-box, we guess some base to reduce the complexity.
Okay, thank you.
Thank you.
Okay, thank you. Please thank the speaker again. We'll move to the third talk. So the third and last talk of this session will be given by Yosuke Todo from NTT and is about Shasha.
Okay, thanks a lot. Thanks a lot for the introduction. So I'm can you hear me? Okay. I'm Yosuke Todo, and this is a joint work with San Antonio Flores Gutierrez. So the topic is about, yes, Chacha. Okay, so first, this is the overview of my talk. Chacha was proposed in 2008, and based on the ARX, and it's a stream cipher. So I think, so RC4 is now sort of very broken, so probably Chacha is one of the most deployed stream ciphers so far. So cryptanalysis of Chacha is a very important research topic. But so far, the most successful and maybe only the successful attack strategy is based on the probabilistic neutral bits. This was proposed by Olmston et al. At the FSC 2008. But one issue about this technique is PNB is almost totally experimental black box analysis. So here we have motivation. So usually, for example, if you attack AES, we exploit the round function of AES, and we always analyze inside of the structure. But now, so in this PNB, it's a black box analysis. So it means that theoretical in-depth, our cryptographers' analysis didn't achieve better result than black box experimental analysis. But I can't accept this situation, so I want to analyze this construction theoretically. So now, so that we focus on the puncturing technique, so we proposed Eurocrypt last year. And the puncturing technique is very similar to probabilistic neutral bits because puncturing is also the approximation of the key recovery map. So the concept is very similar. So now we want to use puncturing for the Chacha. And puncturing is a theoretical analysis so that we can expect we can improve the attack. But unfortunately, it's a bit difficult to apply puncturing technique directly, so we propose a new tool, say trade enumeration puncturing, and finally, so that we get a better result for a Chacha, for each round. Okay, so let's go to the main. So first, this is a structure of the Chacha. So internal state consists of the 4 times 4 matrix, and each element takes a 32-bit value. And okay, so this, the right one is quarter round. And for each odd round, we apply this quarter round for each column. And for every even round, we apply the same quarter round for each diagonal. And finally, after R rounds, so we add as an initial state, like this. Okay, so the most successful attack is a differential linear attack. So the differential linear attack, we first prepare the pair of the inputs x and x plus delta, and output mask is a gamma, and differential linear distinguisher exploits the bias of the autocorrelations from delta to gamma. And key recovery attack is we first guess the secret key K and compute the backward from the Z and key and evaluate this parity of the gamma. And if we guess the correct key, of course, so the value is the same as the output of the autocorrelation, so we observe high bias. But we guess incorrect key, we assume random. But here we have problem. So ARX structure is very quick diffusion. So for example, even for the Hamming weight of gamma is very low, but only a few rounds, almost full diffusion. So it means that if we want to compute this key recovery function, we need to guess almost all key bits. But of course, in that case, the attack doesn't work. So PNB's technique is very nice. So the concept is approximation of the key recovery function. So original key recovery function, of course, use output Z and Z prime and also everything of the secret key K. But after approximation, we only use a part of the key. But how to do it? So that we first divide the secret key K into two parts. The one part is a significant key bit, and another is a PNB part. And we just set some constant C for the PNB part. And usually, this constant value is a magic number, so that we just use the all 0. OK, but what is the problem in this PNB technique? So one issue is we never analyze the inside of the E2 carefully. So of course, we first identify the set of PNBs, but usually this set is experimentally obtained. And also, after identifying PNB, we estimate this the backward correlation also experimentally. So almost everything is experimental attack. And also, there is no plausible evidence we set all 0 as a PNB part, because PNB part is a key. So key is, of course, a random, so in the single key setting. But so the attacker, we just said, OK, this key is a 0. But there's no reason. So this is my experiment for the PNB analysis. So this orange histogram is backward correlation where we guess incorrect key. So it's a random. So yes, it's almost random, and it's very nice distribution. It's a normal distribution. But when we guess the key correctly, the distribution is very strange one. Because it's true, because we set some constant for the key as a PNB part. And if the real key is fortunately very similar to the preset constant, then it's high bias. And very different is a low correlation. OK, so now new theory and new tool. So we use puncturing. So we proposed this technique, Eurocrypt, last year. So the time is limited, so I only express this high-level idea. So first is we have key recovery function f. So f is a Boolean function. And the core analysis of the puncturing is we focus on the whole spectrum of f instead of the Boolean function f directly. And we just force some non-zero entry of the whole spectrum to 0. So this is the example. So the g hat u is equal to the f at u or just 0. In that case, so we can evaluate the correlation between the punctured key recovery function g and the original function f by this equation, rho square. So of course, if we use the original key recovery function f, then correlation is, of course, 1. But now, so that we use g instead of the f. So in that case, we need rho 2 to the minus 2 times data complexity is required. But puncturing can exclude some key bits from the key recovery map. So in that case, so we don't need many key bits if we use the puncturing key recovery function. Okay, so now we want to apply this idea to ARX, but we have problem. So for example, now we want to compute the A double prime 12 from the Z and key. So if we want to apply the puncturing, we need to know word spectrum. But how to know the word spectrum? So the most trivial idea is we first construct the key recovery functions F and apply the word transform. Then, of course, we get a word spectrum. But in this case, this key recovery function involves 83-bit output and 57-bit key. So it means the key recovery function is very big domain, and it's not possible to obtain the corresponding word spectrum. So we need to solve this issue. But it's not so difficult, so we have useful observations. So each Walsh coefficient is the correlation of a linear approximation. And it can be computed as the sum of the signed correlation of all linear trail in the approximation's linear. So it means that we just enumerate linear trail with very high correlation. And enumerating such trails, and finally we get the approximation version of the puncturing word spectrum. So we say this technique is a trail enumeration puncturing. Okay, so this is an example. So now we want to compute A double prime 12. So we first set the linear mask to identify this bit. And first, we analyze the first modular additions. And by using the linear trail transition rule for the modular addition, we get this 26 linear mask. And then next, we analyze the next modular addition. And finally, we get 8 coefficients. Here, so that if we have multiple different input linear masks transit to the same output linear mask, then, of course, the correlation is a sum. So it's a linear Hall effect. OK, so finally, we analyze the last key addition part. And we guess only 4-bit key. In that case, we have 768 coefficients, and the dimension is only 2 to the 10. And the puncturing coefficient in this case is 2 to the minus 6.17. So we need 2 to the 6.17 times data in this case. OK, so finally, we apply the first Walsh-Hadamard transform, and then we got the key recovery, punctured key recovery function. So the original function used the 83-bit output and the 57-bit key. But after puncturing, this function only used 6-bit output and 4-bit key. But of course, this is approximation. We need more data to get the attack, and we need 2 to the 6.17 times data. OK, so this is a high-level summary between the PNB and this puncturing. So PNB is experimental, but puncturing is a theoretical analysis of the linear trail. And PNB's each output is a boot, so 0 or 1, even after the approximations. But the puncturing is a real value, and this real value is theoretically average value over all value of punctured key output bits. OK, so now we apply this technique to Cha-Cha 6. So we first use existing differential linear distinguisher. So the first round differential probability is 2 to the minus 5, and the autocorrelation is 2 to the minus 8.3. OK, so now key recovery function. So key recovery function can be decomposed into the sum of the 20 functions. So it's just so the distribution output linear mask is transit to the linear mask for the known path, and so some bit is involved as a key, and one big thing is these 2 red target bits. So these 2 target bits involve more than 1 modular addition. But others involve only 1 modular addition, and the only analyzing 1 modular addition is super simple, so we don't explain it. So for this bit, This red line is diffusion. And so that we analyze this linear trade. And OK, so this is analysis of the linear trade. And when we guess 4-bit key, so we have 2 to the minus 2.31 correlations. And also for F2, we have the same analysis, and we get 2 to the minus 1.23 correlations, and also the guess on 4-bit key. But one interesting thing is for K1065 is already guessed in the first part here. OK, so this is the experimental result. So we use the 2 to the 12 samples and 1,000 round random keys and a 6-bit guess for F1 and F2. And we compare the PNB and puncturing. The left one is a puncturing. So yeah, so the variance is a bit wider than theoretical estimation, but average is the best nice estimation. But in the case of the PNB, clearly we cannot distinguish anything. And for example, if we guess more key bits, 30-bit key guess, so then of course we have a more accurate key recovery, accurate approximations, and the distribution is much nice too. In that case, so the puncturing is a very nice experimental result, and the experimental one for the PNB, yeah, we can distinguish maybe, but yeah, clearly puncturing is much better. OK, so this is summary of its talk. So we can improve almost 30-bit or 20-bit improvement from the existing work. And we propose a new tool to analyze the cha-cha. So I hope no more PNB. So PNB is experimental analysis, but now we can do theoretically evaluate the key recovery function. So we should use puncturing from now. And we can get a significant improvement for cha-cha. And of course, we have open question. So how to automate this analysis? So probably when we attack the differential attack, linear attack, we use a MIRP-SAT CP solver, and everything is automated, and we get optimal attack. But now we cannot have such a model. So everything is a heuristic. So actually, the puncturing itself is a theoretical, but the parameter is just our heuristic. Thanks a lot.
Thank you very much, Yosuke, for this very interesting talk. Is there any question? I can ask a quick one. I don't really know like linear attacks, but is puncturing the equivalent of probabilistic extension for differential attacks? It looks like
Probably differential attack?
For differential attacks, sometimes we can have like a probabilistic extension of the distinguisher to remove some key material in the key recovery.
For the key recovery part.
Yes. It looks a bit like.
I think it's very similar, but of course, the puncturing is a linear attack. So and yeah, so actually puncturing is the very same concept, but a linear attack, and so maybe a probabilistic extensions is the same similar technique for the differential. Yeah. I think. Yeah.
But here it's completely different to search for puncturing trails than for linear trails.
Yeah, it's a linear trail, so I think it's a bit different. So the key recovery for the differential and the key recovery for the linear is a bit different. So so similarly, so it's a bit different. Okay. Yeah.
Okay. Is there any other question? No? So please thanks Yosuke again and all the speakers of the session. Thank you.